Let's talk about how we use the three primary characteristics of waves to encode information in them for communication purposes or digital communication. Digital means we're using ones and zeros. So how do we turn those different characteristics of a wave by modulating them? Or in other words, modulation means changing. By changing them so that we can represent ones and zeros. Well, the first one we have is amplitude shift keying, or ASK. In this case, I might use one amplitude, let's say this really high large amplitude to represent 1 and this small one to represent 0. So I can have ones and zeros represented. Now I could easily change these around, and there are some protocols and some systems that use the large amplitude as 0 and the small amplitude as 1. There are even other protocols that mean when I change from one to the other represents a 0 or a 1 in a given period of time. By the way, we call this the baud rate. Each change is a baud. And then if we have 4 changes in a second, I have a baud rate of 4. So that's what we mean when we use that word baud, which we haven't really used as much since the early days of modems when we changed audio signals into digital information. But we still use this. In fact, you've probably heard of AM radio, right? That's changing or modulating the amplitude of a wave in order to carry information. But in this case, we're just going to call these digital information. Large is 1, small is 0 in this case. All right, the next one we have is frequency shift keying, or FSK. So we can say that, say, a high frequency is 0 and a low frequency is 1. Or again, we could swap them around, or we could even say, well, only when it changes from high to low is it a 0 or a 1. The third is phase shift keying. So in this case, we have a phase going on. All of a sudden, we change phases just like that. And by changing that phase, we can represent a 0 or a 1. We can say, well, when it's in this phase, it's a 1. And when it's in this phase, it's a 0. This would be a 0 degree. This one is a 180 degree. So every time I go from 0 to 180, then I have created either a 1 or a 0. And again, we could say, well, the change in phase itself forms the 0 or the 1, if we want to do that. One thing we can do, by the way, with phase that we really can't do easily with amplitude and frequency is that we can represent more than 2 different phases. We can do 0, 90, 180, and 270, for example, and get more information out of it. So let's take a look at that. In this case, I've got different phases. This is a 0 degree phase. This would be a 180 phase. This would be a 90 degree phase, and then this one would be a 270 degree phase. Well, now I have 4 different states, so I could represent double the amount of data. I could actually, it's 4 times the amount of data, because I can represent 0, 1, 2, or 3 at any given period in time by representing 2 bits here. So as you can see, each phase can represent 2 bits because I have 4 possibilities. So that would be called quadrature phase shift keying. This is not a separate one. I'm rolling this into, I'm saying that we have 4. The first is amplitude, the second is frequency, and the third is phase. Now I do have one other one though, a 4th one, and that is something we're going to call quadrature amplitude modulation. What we do in this is combine amplitude and phase. So by combining amplitude and phase, I can create a whole bunch of different possibilities. And each of these different possibilities during a given period in time, say from 0 to 10 or 10 to 20 or 20 to 30, I can represent a whole bunch of different possible combinations of ones and zeros. And especially if I'm using quadrature phase, then I have even more, because I've got 4 possibilities in phase and 2 possibilities in amplitude. So that means 4 times 2 is 8. I can get up to 8 different bits and 8 different bits would give us 16 possible combinations. So as you can see, I can cram a whole lot of information into this QAM, or quadrature amplitude modulation.